Hello everyone, my name is Gyozo Akamine. I'm an undergraduate student. Today I'd like to talk about my study. My presentation title is Water Content Measurement in Colonified Layer by Terahertz Spectroscopy. What is background? Our skin consists of 3 layers. They are hypodermis, and dermis, and epidermis. Especially, epidermis is composed of 4 layers, and the colonified layer is the uppermost layer of our skin. And it has many important functions. For example, it prevents water loss from our body, or it prevents invasion of microorganisms or chemical agent into our body. And the water in the colonified layer also have important function, and it keeps structure of colonified layer, and it changes permeability of skin, and it alters enzyme activity in the colonified layer, and it maintains polish of skin, and it keeps transparency of skin. So measuring water content in the colonified layer would be of great help in some cosmetics or medicines or biological research program. For example, polish of skin or transparency of skin is important for cosmetics when making cosmetics, or the permeability of skin is also important in making medicines. And by measuring water content in the colonified layer, we can assume the skin condition, for example, atopic dermatitis or the burn condition skin. The traditional method of measuring water content in colonified layer is measuring of electric conductance, or the electrostatic capacity, or NRI, or measurement of transdermal water loss, or the Raman spectroscopy. However, there are some programs in this method. For example, the measurement depth of some of this method is limited, or we cannot measure the precise water content in colonified layer after applying cosmetics or medicines. So, not affected by because of the ingredient of cosmetics or medicines, we cannot measure the precise water content in colonified layer. So not affected by other material, or having adequate measurement depth method is necessary. So I want to measure the water content in colonified layer by using terahertz time domain attenuate total reflection spectroscopy. When the terahertz wave radiated into the ATR prism and reflected totally, the evanescent wave appears on the surface of the ATR prism. The evanescent wave penetrates up to the prism and come back into the prism. Thanks to this evanescent wave, we can get information in depth direction about the dozens micrometers of the depth, and the terahertz wave is sensitive to water. So, and by using the ATR system, we can measure the high absorption material accurately. So by using this method, I want to measure the water content in the colonified layer. In fact, the penetration depth of the evanescent wave, it differs by frequency inverse proportionally. So if I want to measure only colonified layer information, I need to find suitable frequency for colonified layer measurement. So to achieve this, I introduce contribution rate. Contribution rate is a contribution of a layer on the surface of the prism of a certain thickness to the total absorbance. The contribution rate is calculated by this equation, and by calculating the contribution rate, we can estimate measuring depth of each frequency. So I conducted model experiment. I put the film on the prism and measure absorbance by changing the thickness of film from 0 to 100 micrometer, and I put the water on the film. Then I make some layer structure Then, from the result of absorbance, I calculated the contribution rate. This is the result. The line is a theoretical data calculated by the theoretical equation, and the dot is experimental data. I get this model experiment. You can see there, I show the result at 0.5 terahertz and 1.0 terahertz and 1.5 terahertz. You can see there is high correspondence between the theoretical and the experimental data. So from these data, it is suggested that we can measure only specific thickness in the multilayer material. For example, if I want to measure the 40 micrometer thickness material, in the 0.5 terahertz, the contribution rate is about 19%. So other 10% is contains other information over the 40 micrometer. In 1.0 terahertz, the contribution rate is almost 100. So in 1.0 terahertz, we can measure only 40 micrometer thickness material. Then I measure the real epidermal tissue. I use the human epidermal tissue model for this experiment. The colonified layer is about 5000 micrometer, and the other layer thickness is about also 50 micrometer. And firstly, I put the epidermal tissue in the desiccator for 0 to 6 minutes, and I change the water content in colonified layer by putting epidermal tissue in the desiccator, and I put epidermal tissue on the ATR prism and measure absorbance. To get only colonified layer information, I calculated the contribution rate. The over 0.7 terahertz, the contribution rate is higher than 95%, so I regard over 0.7 terahertz region contain only colonified layer information. This is the result. I show the over 0.7 terahertz region. As you can see, the absorbance decrease as the time I put the epidermal tissue in the desiccator increase. The water content in the colonified layer may decrease as drying time increase. So this data suggests that we can measure it is possible to measure the water content. It is possible to sense the water content in the colonified layer by using terahertz spectroscopy. So next run, I will measure the real water content in the colonified layer and find the correlation between the absorbance and the real water content in the colonified layer. To calculate the contribution rate, I need to know the precise thickness of the colonified layer. So I will measure the precise thickness of colonified layer, and if the position I put the epidermal tissue on the prism is different, or if there is air between the prism and the epidermal tissue, the result will be changed. So, there is also evaporation effect. So the measurement time is limited because of the evaporation from epidermal tissue. So I need to establish ideal condition for water content measurement. Thank you for listening.